The other set of generating functions is known as exponential generating functions. This is different from the ordinary generating functions previously discussed in the first parts of this playlist. Now let's focus ourselves on the form of the exponential generating function, its equivalent power series, and probably its equivalent identity later on, which will be used also to prove other identities and to solve specific relatable problems. So this is how we define exponential generating function. The exponential generating function for the sequence of numbers, okay, so similar, we can have here sequence of numbers, let's say a sub r, which gives us a sequence of a sub 0, a sub 1, a sub 2, and up to a sub r, and still so on and so forth, is defined to be the power series in this form. You have f of x be equal to a sub 0 plus a sub 1 x to the over x to the power of 1 over 1 factorial plus a sub 2 x squared over 2 factorial plus a sub 3 x cubed over 3 factorial plus dot 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 until you have a sub r x to the power of r over r factorial plus so on and so forth, which could be written as a power series, the summation of a sub r x to the power of r over r factorial as r starts from 0 until positive infinity. This is the form of the exponential generating function. The only difference, or not the only, the difference from this, from the ordinary generating function, is that for every numerical coefficient here, there exists r factorial for the or whatever value of r you use. Because in the previous generating function, the ordinary, we don't have all of this, simply all of that in without the factorial notation. But this time, for exponential generating function, we will have this specific form. Similarly, for our power series, we don't have this for ordinary function, but this time we have here again the to be divided, whatever the terms are, to be divided by r factorial. This is actually unique because for ordinary generating functions, the number of ways, still the same here, the number of ways to arrange a certain r objects is the coefficient a sub r. This is still the coefficient and still equivalent to the number of ways of using r or arrangements. Now the additional difference is for the ordinary generating function. Okay, the order of our such arrangements doesn't matter. That's why it's closely similar to combination of all the given r members or r selections. But for exponential generating function, here order is essential, or order is taken into consideration. This is why we have here sets of r factorials per term to meet that standard. So we'll have an illustration for this in the next video and some examples later on, especially some identities which uses this form. Thank you very much for watching.